Hello, everyone, and welcome. Today, we are going to unlock the secrets hidden inside literally everything around us. Yep, we're diving into matter and the amazing energy that makes it all tick. Let's get right into it. Hey there, amazing students. I'm Mr. Saad Wasel, and I am so glad you're here with me. Seriously, I'm so excited because today, we are going to become energy detectives. We're going to uncover some of the coolest secrets in the entire universe. So, are you ready? Let's go. Okay. Let's kick things off with a little mystery. Picture this. On one hand, you've got a solid, cold block of ice. And on the other, a hot, totally invisible cloud of steam. I mean, they seem like complete opposites, right? But what if I told you they're basically the same thing, just wearing different outfits? Stick with me, and by the end of this, you'll know exactly how that's even possible. So, to solve our little ice and steam mystery, we first need to learn a secret language, the language of science. And this language, well, it's all about the energy of these teeny tiny particles that make up, well, everything. Okay, first word in our new language, kinetic energy. Now that sounds fancy, but it just means the energy of motion. And here's the mind-blowing part. Nothing is ever completely still. Even in that solid table in front of you, tiny particles are always vibrating, always wiggling. You could say everything around us is doing a constant little dance. Next up, thermal energy. Now, I really want you to look at that word on the slide, total. Thermal energy isn't just about one little particle dancing. It's the grand total of all the wiggles and jiggles from every single particle in an object, all added together. Think of it like the total energy of the whole team, not just one player. Now for a really important one, heat. You know, we often say things have heat, but that's not quite right. Heat isn't something an object can just hold on to. It's an action. It's the transfer of that thermal energy, and it only flows one way, from something warmer to something cooler. So heat is really just energy on the move. And that brings us to temperature. So if thermal energy is the total energy, temperature is the average. Yep, that's the key difference. When you touch something and you think, ooh, that's hot, or brr, that's cold, what you're actually feeling is the average speed of that invisible particle dance. Temperature is just our way of measuring how fast those particles are moving, on average. Okay, let's put this all together. Picture this, a giant swimming pool and a tiny cup of boiling hot tea. Now that tea has a super high temperature, right? That means its particles are moving incredibly fast on average. But the swimming pool, even if it feels cooler, has trillions and trillions more water particles in it. So if you add up the total kinetic energy of all those particles, the pool actually has way more thermal energy. So remember, temperature is the average, thermal energy is the total. All right, now that we know the language of energy, let's see how it's the boss of the states of matter we see every single day. We're going to look at the big three: solid, liquid, and gas. First up, solids. So in a solid, like ice, the particles are like students sitting perfectly still at their desks in a classroom. They're packed together, super organized. They can't just get up and walk around, but they're not frozen. They can still wiggle and vibrate right there in their seats. Because they move the least, solids have the least amount of thermal energy. Now let's add some more energy. What happens? We get a liquid. This is like the classroom during a break. The students can get up, walk around, and slide past each other. They're all still pretty close, but they're not stuck in one spot anymore. Liquids have more freedom, which means they have more thermal energy than solids do. Okay, but what happens if we give those particles a huge boost of energy? We get a gas! This is like recess time. The bell rings and the students just burst out onto the playground. They're running around like crazy in all directions with tons of space between them. Gas particles have the most energy, and they'll expand and fly around to fill up whatever space they're in. This chart here kind of sums up the whole story. Just look at the rows. As we go from solid to liquid to gas, you see the particle movement goes from vibrating to sliding to just flying everywhere. This also changes their shape and volume. And what's the one thing causing all this change? Look at that bottom row, thermal energy. The more energy you add, the more everything changes. It all comes back to energy. So wait a minute. If energy is the key, does that mean we can actually control the states of matter? Can we change them? Absolutely. We can make matter change its form just by adding or taking away thermal energy. Let's see exactly how that works. Let's follow the journey of water. We start with solid ice, right? The particles are just vibrating with low energy. Then, step 2, we add heat. The particles start vibrating faster and faster until they break free from their spots. That's melting. Now we have liquid water. But we're not done. Step 4, add even more heat. The particles move so fast, they literally fly right out of the water. That's boiling. And now we have steam, a gas. It's a simple path, all powered by adding more and more energy. No, this isn't just stuff that happens in a science lab. You see these ideas in action all the time, especially in the kitchen. Let's connect all this science to the real world. Let's think about something simple, like holding an ice cube. Why does it melt in your hand? Well, because your hand is warmer than the ice. And what do we learn? Heat always transfers from warmer to cooler. So thermal energy flows from your hand into the ice cube. This gives the ice particles more kinetic energy, they vibrate faster and faster, and poof, it melts. You are literally giving your energy to that ice cube. Okay, let's put on our thinking caps. We know heat transfers from warm to cool. A hot tray straight out of the oven is way, way warmer than your hand. So, what do you think would happen if you just grabbed it? And more importantly, how in the world does a puffy oven mitt protect you? Well, here's the secret. The oven mitt is an insulator. That's a fancy word for something that's really bad at transferring thermal energy. It acts like a roadblock for heat. It slows that energy transfer way, way down, so the heat from the tray can't rush into your hand. It gives you time to put the tray down safely before you get burned. It's science acting like your own personal superhero shield. So you see? Understanding energy helps us understand and even control the world around us. The handle on a hot pot, the thermos that keeps your drink warm, the cooler you take on a picnic, they all work by controlling that transfer of heat. So here's your final mission, energy detective. Look around your world with your new science eyes. What other heat protectors, what other insulators can you find? The secrets of matter are absolutely everywhere, just waiting for you to discover them.